Good afternoon. We probably experienced a brief disruption about our CAT course website, right? Can you guys hear me now? Chat box is here. Okay, good. Thank you. Yeah, it's good. So today is a good day. Why? Because all professors, all staff on campus will receive the vaccine, and all graduate students. So for undergraduate students, maybe just wait another few minutes, a few days. So it's going to happen very quick. So that said, we see the end of the tunnel. We are going to get through this pandemic. You know why? Texas already removed all the orders of mask or whatever restrictions, all open. So, no, rest in peace. I think it's a little bit aggressive. Yeah, we'll see. I'm happy they are doing a bad example for the bad consequence. We'll see. Doing an experiment using real life. So anyway, so I think we are optimistic now and then ever. We are going to be get through this one together. So soon. So welcome to week number 7, lecture A, and we are in the last week of our signals and systems. We have learned quite a lot of skills about analyzing a dynamic system in both time domain and frequency domain. So today we are going to, again, a little bit slow down and to consolidate what we have learned and a few knowledge gaps we're still facing that I believe they are very basic to all of you. So first of all, please get a copy of the quiz. We are going to run through that quiz together today with you. And other parts of today, we are going to go through the stability checking again, okay? And we are going to do how to read a Bode plot, okay? So giving transfer function, you should be able to do a Bode plot. Then giving a Bode plot, can you write a transfer function? So we are going to do a practice on that. And we are going to explain a little bit more on convolution, signal system concept. So, and time frequency domain response. Also, we haven't done two things. One is Bode plot for second order system. And the one is how we deal with partial fraction expansion using when we have a pole with a multiplicity more than 1. So we're going to go one by one, okay? First of all, let's take a look of a question in front of you. Can you read? Oh, I haven't shared my screen, did I? No, I didn't. Okay, here we go. Hide floatings. Do you see my screen? You have a transfer function here, right? You have a transfer function here. And this is a question about 30% of the weight in 100% of this exam paper for PhD preliminary exam to check whether they are doing a good job in their in the basic control signal systems and controls. So you can see that first one is sketch the gain and phase Bode plot asymptotes. Okay, what do we mean asymptotes? Is those lines, straight lines, okay, straight lines. Then derive its impulse response time function. You can use Laplace transformation table given, okay. After that, there's 2 sub-questions regarding control the system. So we assume this G is a open loop transfer function, of a plant to be controlled. Then we use a proportional controller using a negative feedback unity. Then so something like this. So let me see if I can do it. Yeah, I can. So I put this is a system, I put this is output, this is the input. So this is called open loop, right? It's open loop. Then I pull out the feedback, okay? Then here, this is a unity, meaning this is a 1, okay? This is a 1. You can drop this one, but to just show this is a unity. Then you do feedback, okay? So this is negative feedback. So you have a reference here, okay? Reference here. So then I forgot to put a controller here. So you have controller. Controller is a KP, just a gain, okay? KP. So the question was, this is the signal of E, arrow. And can you tell me what is the E infinity? Okay. So can you tell me now? So I think after 2 weeks, you will be able immediately to tell me this is 0. I said it's always 0. So why you can immediately tell? Okay, so we're going to learn next week. So then if you say, oh, I'm not using a step, I'm using a ramp actually. Ramp is T, step is 1, okay? If I have a ramp as a reference, then the E is no longer, this is no longer 0. So then I want you to find out what is the E infinity. E infinity is also called a steady state arrow, okay? So that will be, you will be able to do this one immediately. Very simple, okay? Then you do open loop transfer function of plan, use proportional and integral controller. So you have this one, okay? This is a PI control, proportional and integral controller. So then I want you to check the stability, because if you choose KPKI arbitrarily, you will mess up the system becoming unstable. Then you need to learn how to use the Roos table, okay? How to use the Roos table. What's that? We're going to learn next time, okay? Just give you a preview. So these are considered as a very fundamental skills. If you cannot do that, yeah, you probably should not do a PhD. Let's give you an appreciation how fundamental things these are, okay? So with that said, let's go back to the quiz, today's quiz. So let's check the stability. The rule of a system to be stable, the first thing first, you check its position in a complex plane. This is a real, this is imaginary. This is imaginary, okay? So for the first one, you can see what are the poles. You have a -1, -2. Then you have a -2. You also have a -1, right? But you have 2 -1. You put a 2 here, a 2x here. But what about d square? This one can be written as a d plus 1 square plus 1, right? Then square. So for this one equals 0, then what is the pole? It's a -1 plus or minus j, okay? And you have 2 of them. So you have, this is a -1, this is a minus j, this is a plus j. So you will have a pair of poles in here. So you are on the left half plane, okay? So the whole thing is stable, even if you have a multiplicity 2 here. So it doesn't matter how many multiplicity you have, okay? So you put this one 100, it's fine, okay? It's still stable, or left half plane. Understand? So the first one is stable, okay? How about the second one? Second one, we are going to draw. The first one is d squared plus 1. You will get you a minus j and plus j. Right? The second one is -1, and you have another -1 here, okay, multiplicity. So this multiplicity doesn't matter. You can put the 2000 here. It's okay. Okay. So it will still be stable. And here you have one pair of complex complex conjugate root on the imaginary axis. So you only have one, and you only have one multiplicity in here. Okay. So the whole thing should be what? Because there is one not on the left half plane. So it is critically stable. Okay. Critically stable. Okay. The same thing applies to the number 3. Is also critically stable. Okay. All right. So now you have this one here. So you have this term. You have this term. It's a -1 plus 1. -1j plus 1j. So you got to cut off for a bit. So why again? Okay. This one again means you have the same complex conjugate pair in here. Okay. So that's why it's critically stable. It's not considered as stable or unstable. It's in between. Okay. So number 1 and then number 2 and number 3, 2 and 3 is essentially the same thing. So number 4, we have this one. This one is complex conjugate pair on the imaginary axis. So you have one pair, but you have a multiplicity 2 in here. That already will make my system unstable. Why? Because you remember, this one is linked to my sine t. Okay. Well, if you have sine t is critically stable. Okay, it's not blow up, not going to 0. So if you put a square in here, you are going to have another t in here. Okay, so that t will blow the system up. Okay, so that's why this is unstable. This is unstable for sure. But what about this one? About this one? This one is -1. Is one pair in here. That doesn't matter how many multiplicity in here. So these poles are stable, but you have unstable modes. So the whole thing is unstable. Okay. Okay, so that's number 4. So you can summarize some of the rules. I'm not going to do that bullet list. So basically, you check all the pole location. If anything on the right half plane, that's unstable. If all in the left half plane, no matter how many multiplicities you have, it is all stable. The distinguishing case is when you have a pair of poles that is complex conjugate and on the imaginary axis with more than one multiplicity, then it is unstable. It's this case. In this case, it's unstable. So let's check number 5. Okay, so number 5, let's draw here. So this is a 5. Number 5 will give me, so you have -1. This is a -1. You have multiplicity 2. Okay, multiplicity 2. Doesn't matter. This is stable. How about the other one? The other one is -1. You have this one, and you have multiplicity here. So this case is a stable case. Okay, it's a stable case. So I want to ask, is this a stable case? No. It's not an unstable case? No. Because there's only one complex conjugate pair on the imaginary axis, so it is critically stable. So I'll let you digest a little bit on this and make a note. So in the future, no matter how you change, you should be able to tell stable and unstable, okay? And the critical stable. Okay, so just to show that if I put here like 2 multiplicity, then it will be unstable, okay? So because you are going to have a multiplicity here, okay? Okay, so, all right. So, so this one is to give you a chance to sketch body plot, okay? Sketch body plot. So last time we only did this case, right? This case. I think you should be able to do that. Let me remind you what we did. It's quiz B. Oh, let me smaller. Did you see that we did this one? S+1 divided by S+10. I also tried to tell you how to do to switch them, okay? To switch them. I hope you can capture everything here. So there are 4. One is lead, one is lag, okay? So for example, our original one is a lead. It's a lead. The black one is a lead, okay? So you can see the phase is here, okay? It's positive. It's give you some leading phase. But if you switch, then you will have lag first, then lead. So you lag first, then come back. So lag, lead, lead, lag. So let me try. So S plus, no, it's too big. So let me see, you have a S plus A divided by S plus B, okay? S plus B. So which one is lead? So A greater than B, then it's a lag, okay? A less than B, then it's A less than B, then it's lead. Sorry, A greater than B is lag, then it's lead. So this is the case for the black one, A less than. A is 1, B is 10. So this is the black one here, okay, black one here. So the phase is from 0 to bigger and to 0 again. Okay. So today we are going to do something a little bit different. So I didn't change anything here. I only changed the sign here. Did you see that? This is the sign I need to change. Okay. So this is called non-minimum phase because in this case, so the first case is you have -1 in here, you have -10 in here. You have one pole. Oh, sorry. No. This is 0. 0 is using a circle. A pole is a cross. Okay. Well, that one is different. So you have -10 here, -10 cross, but your pole is here. So your 0 is here. Is a +1. So it's called right half plane 0. Then we keep saying that is a non-minimum phase. Why we say that? Why we say that? Now I'm going to show you. I did some homework for you. I'm going to show you non-minimum phase 0. Where is it? Okay. From this, you can see that we have a different system here. So one is, so like this one, so you can see there's, you cannot see it very well, but I'm going to draw this one to you. So this is one system. This is another system. So this is like, actually the code is here. The code is here. So you can see that the first one, you have 1, 1, meaning s plus 1, and you have 10s plus, s plus, yeah. It's a system 1 is transfer function 1, 1 is like this numerator, and then you have 10s plus 1, right? The 10 plus 1, you should write like s divided by 1. You have s divided by 0.1, right? Okay, so, right? The second one is like you have a minus s plus 1. You have the same s plus 1, right? So the same thing I should say s divided by minus 1 plus 1, s divided by 0.1 plus 1. So I'm doing the Bode plot for you. So you can see that I changed the sign here. I changed the sign here compared to this one. But if you want to do a magnitude, so you can see that if S is j omega, so the magnitude of this one is omega squared plus 1, okay? This is omega divided by 0.1 squared plus 1. So this is magnitude. So the whole magnitude is like this. Do you think this is the same? Because you have j omega, then you have an imaginary part. After you do the square, it's the same. So that's why in this one, the magnitude in here are the same, okay, are the same. Let me do the full screen here. So the difference is, so again, this is plus or minus s plus 1, the s divided by 0.1, and plus 1. So you can see that this is lag, okay? This is a lag filter. Okay, this is a lag filter because A greater than B, okay? A greater than B. Okay. So because you will go to the lag first. So this is like 0.1, okay? So then this is 1, okay? This is 1 here. This is 0.1. So this 0.1 will correspond to this point is 45 degrees. So this is my minus 3 dB in here. So minus 3 dB in here. So I didn't draw the asymptotes. What is the asymptote? So you should draw this one until 2.1, the first corner frequency. This is the corner frequency. Then I'm going to go down, okay? I'm going to go down and the minus 20 dB per decade. So this is a minus 20 dB. So this is 0.1. Then this is 10. This is 1. Okay, this is 1. So from here, there's a 1 decade. So I should do this. Then you do this. Okay, you do this. So this is slope is minus 20 dB per decade. Okay, per decade. So this one is actually called asymptotes. Okay. Asymptotic lines, asymptotes. So this small one here, this is a minus 3 dB, okay? Minus 3 dB. And this corresponding to here, so this is 0, this is also 0. So this is 45, this is also 45. So it's a lag filter, okay, lag filter. So this is the one when it is positive 1. So it's s plus 1, s.1 plus 1. But this one is different, you can see. You have a minus sign in there. So they start with 360, okay? Then they will go down like this. So it's non-minimum. It's called non-minimum phase. That's why it's big. Okay, it's non-minimum phase. Okay. This one is the same, which is s divided by 0.1 plus 1, s divided by 1 plus 1. So this is a plus or minus, okay? So you can see the phase is leading, it's bigger than 0. So this is lead than lag, okay? So the same thing here, you have 0.1, you have 1, okay? So this one will be 0.1 and 0.1. So you got 0.1 and 1, 1, 1, 0.1, minus 1. Yeah, so this is a 10, remember? This is a 0.1. So by doing that, you see the phase also is way up in here because of the sign. So that's why it's called non-minimum, okay, non-minimum. So this is a minimum phase, non-minimum. So then I do a step response, I do impulse response. So you can see there's some getting to the negative direction first, okay? So minimum phase and non-minimum phase, they do have very different behavior in time domain as well as in the frequency domain. So you should identify that. And in the end, eventually you are going to see that why a system is hard to control is because of this non-minimum phase. So, or when you have a 0 in here, although it's not going to affect my stability, but it will make our control task much harder, okay? So that is for our homework in the quiz, sorry, the quiz questions in here. Any questions at this point? Are you able to draw that for me? Just go a little extra, be careful, okay? Because of this minus sign, I'm not putting in here. There's some difference, okay? Be careful, all right? So you can do left-hand side, no problem. Right-hand side, be careful, okay? So I suggest you can do this one after the class and submit before the midnight, okay? I'm going to finish this one. So let's do the second part, how to read a lag filter and a lead filter. So can you tell me which is, oh yeah, you can see, this is a lead filter because the phase, this is a 0 phase, okay? This is 0 phase. So then this is leading, okay? Bigger than 0. So that's why I call it lead. Phase is sometimes also called phase leading filter, phase lead. You need some phase lead, phase lead. So phase lead, then you are going upwards. So what's the rate? What's the rating here? It's positive 20 dB per decade. Okay. And so how do I know where is my breaking point? I don't have a asymptotes in here. I don't have a asymptotes in here. So I cannot see it clearly. What are you going to do? We know that it will pass at the corner frequency. It will pass 45 or minus 45 in here. So we know that omega is 0.1 here. So this is 0.1. So this is 0.1. So this breaking point should be like this. If you do asymptotes, you should write something like this. Then you go to 20 dB per decade. So this is 2 decades. So this is 1 decade. Okay, this is 1 decade. So this is 1. This is 10. So from 0.1 to here, so you have 2 decades. 2 decades, you'll be 40 dB. Yeah, 40 dB. So you should connect this line. Okay. Then you do this again. So this red line is called a asymptotic line. Usually you don't have the accurate to draw this green line. It's not needed. So you only draw this asymptotic line. So in this case, I know that I have a 0 then going up. So I definitely have S divided by 0.1 plus 1. Then when I'm going to break it, is when the break point is, this is another 45 degrees. So I have break point at here corresponding to 10. So this will be S divided by 10 plus 1. Okay. So because this is 0, be careful, this is 0. Therefore, when omega is 0, then the whole thing is 1 divided by 1. So we'll give a 0 dB, right? So this is correct. So this is correct. So the transfer function for this one, this green one is like this. For the blue one, we do the same. We do the same. This is so symmetric. So I don't even need to do anything. I just say, oh, S divided by 10 plus 1 plus S divided by 0.1 plus 1. Because I have 0.1, that is here, okay, that's here, 0.1 is here. So I have this breakpoint, then I have 10 in here, okay, so this one, okay, this is my 10, this is my 0.1. So then I just link these 2 lines, is my asymptotes, okay, so it's my asymptotes. Again, this line will be minus 20 dB per decade. The reason is I'm going to meet this guy first, 0.1. So I go down with minus 20 dB. But when I meet omega is 10, I start to have a numerator kick in. So they cancel out the motion, it becomes a constant, okay? Because you go down minus 20 dB. I have now, from this point, I have a you keep going, then you have this one, then you have this one. So you cancel out, you go in the middle, right? So for the first order Bode plot, so now you can see this one will correspond to my magnetic Bode like this. But usually you are not going to work directly on the 100%, the original plot, because it's hard to identify the corner frequency, okay? But using this phase will help you to do this, you can see, okay? So this is called a Bode plot reading, okay? From the real one, or you can read. But on the other hand, I have another example here. I hope you are going to enjoy it, okay? Oh, give me a second. I'll reply. Somebody's urgently wants to meet me, and I think something wrong here. So. Sorry. So this is saying that how to read transfer function from from body plot without asymptotes, okay, without asymptotes. What if you have some asymptotes, okay? What if you have asymptotes? I think I have an example here for you to take a look. Give me a second. I'm here. So do you see asymptotes like this? So you have body plot. So these are the asymptotes, okay? This red lines are asymptotes. And these blue lines are the real body plot. So if I give you the real body plot, it's difficult for you to identify those corner frequencies. Here you can. So usually you will be asked to giving asymptotes, how you can identify the system. So if you are giving this one, what are you going to do? Okay, what are you going to do? So you need to see, let me make it bigger. So you need to see from low frequency to high frequency, you check from this side, okay? So it is always going down. What is a line always going down at minus 20 dB per decade? So this is actually is one of S, it's an integrator, okay? So to counteract the integrator, so you have something like, so assume this is omega-1, this is omega-2, this is omega-3. At this point, it comes to flat. So that means you have S plus 1. Sorry, you have S. So here you are going to have S divided by omega-1 plus 1 term to make this one level. Okay, make sense? After that, you still have going up. So you have another 20 dB per decade. So then that means from here, I know you have S omega-1 plus 1 S. Then you have another term, S divided by omega-2 plus 1, okay? Okay. Then, but in here, you suddenly have omega-3 at this point. You need to break, go down at minus 40 dB, okay? So this is one decade, this is 2 decade. From here to here, so this is minus 20, so here is minus 60, so it's 40 for, so this is just one term, okay? This is just one term, S divided by omega-3. You need to count, you're going up, you have one, if you have only one, then you become a level, right? But you even go down, that means you have 2 terms, okay? You have 2 in here. So let me identify. So omega is 0.01, omega-1 is 0.01, and this is omega-2 is 1, omega-3 is 10. Okay, it's 10. Is it 10? Yeah, it is 10. That's it. So what I'm going to do is to write S divided by omega-1, 0.01 plus 1. You have S divided by omega-2 is 1. Okay, but I know there's an S in here. Then I have S divided by 10 plus 1 square. Okay, but remember, if you S is 0, then everything is 1. It should be 0 dB, but it is not 0 dB. Okay, it is not 0 dB. When omega is 1, okay, when omega is 1, you can see when omega is 0, No, it's not going to be 1. It's going to be infinity, all right? So it's infinity. So this is going to infinity. Okay, it's going to go infinity. But how do I know how much I need to shift up and down here? How do I know? That's easy. Without this term, so you check everything. Without this S term, so then you check everything. Okay, check everything. So when omega is, if S goes to 0, then it is minus 40. Okay, minus 40 here. But actually, in our case here, so you are only 1 here, 1 and 1 and 1. Okay, so you need minus 40 dB. Okay, so that means you should have 10 to the power of minus 4. Minus 40 dB is 10 to the power of minus 2. That's the correct answer. Okay, correct answer. That will give you that minus 40 dB going down. Okay. All right. So let's check what we have. Let's check what we have. So the real results is like this. It is actually this one, and you have an S plus 0.01 and 1 plus S. So which is S plus 0.01, S plus 1, S plus 10 square. Okay. Is that right? Did I do anything wrong? Yeah. S plus 10 bracket square. Then you need 100. 100 is minus 40. I already have it. So this term is not needed actually. It's interesting. But anyway, be careful about this term. Okay, we already have it because we write the standard form. If you write this one to here, so you have a 10 here, so that means you can get this, cancel this one out. So cancel this 0.01 out. Yes. So in the end, you have this one here. Okay. Yeah, this one here. How we can draw a body plot. So the body plot, you have learned how to do it, right? But there is also a command called asymptotes to draw this system. The system is called LTI object. I think everybody knows how to do it. Okay, but this one is something special. You should get this code from a place called this one. Okay, it's called Bode plot with asymptotes. So MATLAB Central. So let me give you this one from I'll upload this file for you. You can go to this page, okay? So you can see you have something here, okay? Okay. So then you download this code, a simp, okay? Download this code. Then you should be able to draw something like this, okay? So I'll help you a lot, okay? On the other hand, you can see in the MathWorks here, the top one here, you can click the community, okay? You'll see there are a lot of things about community. One of them, I check it very often, is called file exchange. When you do something, you'll most likely be able to find it. So what do you want to know? So you want to check out anything Dr. Chen contributed to there. Just put my name in here to see what's going to happen. Have you tried? Oh, there are quite a few, right? So see? Yeah, so if you are curious about the stuff I did, you can go there and take a look. Anyway, So we are going slowly down, and let me summarize what we did. We had the appreciation of how to check the stability based on the pole zero location. We reinforced our understanding of non-minimum phase, and also the time frequency demanding. Okay, so then we learn how to read the body plot from how to read the transfer function from the body plot. We did without asymptotes. We did another example with asymptotes, like this. And I showed you there is a MATLAB file function that can do it automatically, beautifully for you. So pretty nice, pretty nice. So what we are going to do next is to do something a little bit more fundamental. Remember I showed you this? So at this point, you should know that giving a signal, whatever mixed, using Fourier series expansion, you should be able to understand what are the harmonics in there. So basically, it's a series of sinusoids, okay? Basically, it's just sinusoids, okay? Expansion at different multiples of fundamental frequency. And you have learned Taylor series. So this is a different series, okay? So the difference is that this Fourier series, okay, Fourier sinusoid basis, they are orthogonal in the sense of these two equations, meaning if they are not the same, they have to be zero. Okay, if they are the same, then it's not zero for this harmonics, okay? It's very interesting, beautiful, elegant. You can write in a compact form like this. Okay, then you can draw the signal magnitude according to the harmonics. You can see that's called frequency contents. All these are like 0.504% of the contents. Okay, and these are the phase. Okay. Okay. So that's a Fourier series method. Now later we said that, oh yeah, Fourier series means you have to make the function and make it as if it is periodical. Then we do this expansion. But usually in practice, we don't do that. So we now look into the Fourier transformation. Okay, then the Fourier transformation, we learned that it is closely linked to Laplace transform when you have S put into replaced as omega. So you have a transfer function, then you have Hj omega. Okay, Hj omega. Okay, so then this Hj omega, you have magnitude, then you have e to the power of minus j. Okay, so this is called magnitude. This is phase. You plot this one and together with a log 10 omega xx. So this is 20 log 10 is a dB. So then this is like a body plot, magnitude body. Then also you have phase body. So magnitude and the phase. So the idea of this one is to allow you to do a system. You have H of S, okay? So then you have input is a sine omega t. Then your output is also a sine omega t, but with a different frequency, a different phase shift and a different amplitude. Phase omega is the same. So this is called frequency response. Frequency response. So this is called frequency response. Frequency response. So, but in your circuit theory, you have learned something called SSS. It's called sinusoid steady state. steady state. Okay, so you have sinusoid going the circuit after a while, and in the steady state, what's the relationship? So you have phasor, you have those complex phasor method. Okay, so it's linked to the impedance. Okay, which is a complex number like this. Okay, like this. All right. Last time I told you that you don't want to do something like this. So like sine omega t. So when you do final value theorem, when t goes to infinity, this is what? If you say, oh, this is a s square plus omega square, then you do final value theorem times s, then you send s to 0, you get a 0. Then this is wrong, right? So you have to have all the poles on the left half plane. So don't make that mistake, because you don't know what is a sine omega, sine infinity. So in a steady state, you will never use final value theorem for that sinusoid. You have to use this frequency response point of view. Okay. All right. So there's no such thing called final value. There's no such thing here. Doesn't make sense. So convolution is something I stopped last time. I upload this one, but it's not easy to read this part. So this is a cartoon shows so hard that this is a dean of engineering, and all the students are trying to protest our dean. Its spark is worse than its spite. Do you know what's the meaning of that? Meaning, just do it, learn it, don't complain. Okay. So what they complain? There's a downways convolution. We shall overcome revolution, and so on and so forth. Not convolution, make love, not the convolution. I like it, it's a joke. So that means convolution is seemingly hard. They even have a sentence in here. So I follow this trail. So this is an article, just one page here, okay? He quoted Lathy is the author of the signal processing textbook I gave you in the last homework. Oh, by the way, we pause for 1 week for homework, unless you insist. So we don't have homework this week, okay? Relax and consolidate all the concepts. Okay? So I'm going to give you a little bit of taste of the convolution today, okay? Convolution today. I know if I give you in the front, you'll quickly lose sense and feel bored and start to protest like in this picture. So I think now is time we can say something about that. So this one said, appears very complicated, okay? That means in reality, it is not that complicated, okay? And so, and convolution is actually a core concept for electrical engineering, or for engineering undergraduate students. And it's called contemplative theology, contemplative theology, and whatever. So in fact, this piece here is very interesting to read. Okay, very interesting to read. I want to highlight something for you. So one of the pioneers doing this Laplace transform, okay, is actually the Heaviside. Okay, you remember Heaviside? We're going to do that. There's another name you should remember. It's called Gustav. Okay, Gustav Deutsch. In 1937, okay, he did a very comprehensive Laplace transform handbook in German. Okay, and the English one is in 1942 in the United States. Okay, So now at that time, the transient analysis becomes popular. So it's not so far away. You guys should learn. And I have a copy of this his book, so it's amazing. Okay, I don't have enough time, but let's move on. So when we say convolution, it's you have two signals, F1 and F2. You put a star in here. That's called convolution integral. So basically, you do from -infinity to infinity and put these two together. So you integrate with whom? With tau, okay? But you actually want to get a t, so your t is fixed, okay? Given t, okay? But remember, this is f tau, and this is a minus tau means your time arrow got, this is a tau, okay? Then this is a minus tau, right? So the time got reversed, okay? So you can just imagine you have like you have two railways, one moving this way, one moving this way. So this is like train, right? Train. So train 1 and the train 2. Okay. And then when you meet, the overlapping part will just get summed up. I'll show you that one later. So the swap of them, so this is called commutative. You swap them, doesn't matter, okay? Doesn't matter according to this definition. And you also can do, this is called linearic distributive, okay? And so if you have associative, meaning doesn't matter of the order, okay? Doesn't matter of the order, okay? And there are some other properties of shifting, okay? So if you have something that is minus tau delayed, so this one also delayed, okay? And if you delay 2, then you got to add together delay. That doesn't matter. And there's another one called impulse. This is a beautiful thing called impulse. So that's why you can see this is impulse. So it's like shifting. So once you impulse with this one, so this delta is non-zero when this is 0. Otherwise, it's 0. Okay. So delta t minus tau is not 0 when t is 0. Okay. And it is 0 when t minus tau is not 0. Okay. So this is a definition. So then I know that I have to choose t is tau. Okay. T is tau. Tau equals t. Okay. Tau equals t. Tau equals t. Otherwise, all 0, I don't care. So that's why this one will give me what? Itself. Okay. Yeah, it's something like this. Okay. As if we didn't do anything. So that's the beauty from the delta. Okay. So now delta is called impulse. Okay. So we keep hearing about impulse response. So you have an impulse, you activate it on the system that is a J, this one here. So this is called H of T, okay? So this is called impulse response. And it is very interesting that, very interesting in the sense that H of S is the Laplace transform of my H of T. Okay, so remember I said something in the beginning. A signal is a signal. A system is a mapping between signal 1 and signal 2. Okay, 2 signals. On the other hand, if we call this is a signal, and we can say that this signal is actually can be regarded as a impulse response of a dynamic system, and its transfer function is a Laplace transformation of the signal. So therefore, a signal could be used to represent the system. So I'm confusing you, I know. So signal is signal, system is system. System is a mapping between signals. On the other hand, a signal can be used to uniquely represent the system, okay? Like impulse response. So that's why we need to study impulse response, because impulse response can be used to represent uniquely one-to-one of this transfer function. Okay, how this is possible? How this is possible? So this is a zero state response of and causality. So you have a system. Basically, you have system. So you have a F, okay, into a system, and you want to get a Y, okay. And how to? What is the system? So I say your system impulse response is H, or it has a transfer function of H of S, okay. So then my output is simply a convolution between this arbitrary input and its impulse response function. So that is given this way, okay? Given this way, okay? Given this way. So this is all connected now, okay? All connected. So I know that my Y can be written in terms of U, but convoluted with my H, okay? Now H is actually the inverse Laplace transform of my capital H of S. I'm not sure you are confused at this point or not. So that's the meaning or reason we need to study convolution, okay? But at least you need to remember the convolution's definition, okay? So this is definition, okay? All right, so let's do an example, okay? Let's do an example, okay? So supposedly you have a system, okay? You have a system that is with all the UT. This UT here is heavy side, okay? Meaning anything anything less than 0 is 0, okay? It's 0. So therefore, the convolution from minus infinity to positive infinity, so you only need to do 0 to t, okay? Okay. Supposedly, you have a system that is S plus 2, 1 over 2. Okay, remember, if I do inverse Laplace transform, it's minus 2t ut, right? So this is my h of t, right? So then I put this one here. I have e to the power of minus t ut as an input. What is my output? Okay, easy. You do convolution. So this is my f. This is my h. My y equals f convoluted with my h. So it's this guy. So this is my h. This is my f. If I convolute this one, I'm going to get my output. So how to do that? So according to the definition here, you write this way. Then from this one, you know that t is fixed. So I just remove here. I do the tau, so you end up with this. Okay. So in the end, you got something like this. Okay. This is my output of my y. Okay. But if I do f tau, so this is f. So this is the same as my f. But now I'm going to do ht minus tau. Okay. Ht minus tau means I need to do f minus tau first. So I just mirror this guy. It's a mirror. It's a reverse time axis. So, but I need to remove, I need to shift this way, such that I shift this way. I got a t in here, okay? Got a t in here, okay? So after that, I'm going to multiply these together. So I let this t move. Let the t move from 0 to infinity. So this is t is a negative. So then there's no intersection, okay? Then integration will be 0, okay? So then you move, this guy is fixed. I don't do anything here, but I allow this one to change, to shift from left to right. So think about, you have two trains meet, right? So this shaded arrow is, everybody can see from each train, that overlapped area you just add together. It's an integration. So you're starting from 0, you don't meet. Now you got to start to meet. Then you meet more. Then you move away. So this is going to 0. So it's going to 0. Okay. So that's a kind of animation. You can find out my animations online yourself. So that's convolution. I hope you are going to accept this convolution. So this picture will connect everything together. Signal and system, and signal can be representing a uniquely a system. The system is a mapping between two signals and so on and so forth. Okay, don't get very confused. So now let's do CUPI. Let's do CUPI. So let's do a CUPI when we have multiplicity here. So as I said, I'm not going to do multiplicity more than 2. Okay. Now this will not happen in our exam, but it could be have 2. Okay, how I can do this. So from this example, you are going to see how we do it. So CUPI meaning if you have one pole with multiplicity 1, this is another pole with multiplicity 3. So you only have, for multiplicity 1, you have 1 term. For multiplicity 3, you have 3 things like this. So it's a 1, 2, and 3, different orders, while everything on the numerator is a constant. Okay, so we are going to CUPI. So I cover s plus 1, cover s plus 1, insert -1. So I'm going to have -1 here. You have 2, -1 here. You have 1 to the power of 3 is 2. Okay. Here is the fun part. Okay, here's fun part. So this one, A0, the highest one, you can use the traditional CUPI. So you cover this third the part, but you do, this is plugged in. So you have a -1 here. Sorry, you have a -1 here. You have -6. So it was +6. So this is a +6. So this is 2. Okay, the +6 done. But how to get this guy, A1? Okay, A1. So okay, how to do? Still do CUPI. So you cover up, but don't plug in yet. Cover up, you do DDS. Okay, do a derivative. Okay, after that, you start to plug in. After you've done the DDS, you do this. Okay, I'm not going to do this one with you here, but the same thing is true for this one, A2. A little bit involved. You need to cover up, don't plug in. You do second order derivative. Okay, second order derivative. Then you plug in, then divided by 1/2. Okay, it's interesting, it's still this one. So let's take a look in the end what I have. I have here, I have here. So because this is e to the power of -2t, e to the power of 2 is because of this one. But if you have a multiplicity, you are going to have a t. If you have another multiplicity, you have another t. So t square, okay, t square. So in this system, I'm asking, is this stable? Yeah, because the pole is -1. You have another one is pi -2. You have another one, you have another one. You have multiplicity 3, multiplicity 1. So they are all in the left half plane. They are all stable. But I told you that you have t goes to infinity. So let's say t square e minus 2t. Is this goes to infinity or just go to 0? That's a good question. So let's do this. So t squared divided by e to t. When t goes to infinity, what do we should do? We do derivative, okay? Then you have a 2t e 2t times 2. So this is still infinity divided by infinity. So you should do one more time, log it down. I have 2 divided by 4e to t. So t goes to infinity, this term will go to 0. This is not true. So in other words, it doesn't matter how many multiplicity you have, t to the n, okay, no matter just the n times of derivative, still you'll get to 0. So this is called exponentially decay. This is called polynomial increase, okay? So who is faster? This one is faster, right? So always, okay, always. So that's why in the left half plane, you don't need to worry about multiplicity. If it is on the left half plane, it is stable, no matter how many multiplicities you may have. Okay, so if I do this, so I have this one here, I have s plus 1, s plus 2 squared. So what is this? So you have k1 divided by s plus 1, then you should plus a 0 s plus 2 square plus a1 s plus 2. Okay. Okay. So this is CUPI. Okay. This is CUPI. So it's also 2, right? So k1 is 2. So for the this one, you do CUPI minus 2. It's still 6. So a0 is 6. Okay. All right. And so if you do here, you have a1 equals, you do derivative here. So it should be the same. So that gives you some impression that, oh, it doesn't matter if this is 3, then they are the same. So they are the same, okay? So that's an illusion, please. So just imagine, if I put this one not 2 minus 1, say, for example, this is 3. No, it's not going to be the same, right? Be careful, okay? So our time is almost up. I think we have done a very good job reviewing the essential concepts. So I want to higher pitch of Oliver Heaviside to you. So he's really good. So you can see from the slides, he's the first to write Maxwell's equation in the modern form. He's an innovator of low pass filter, okay? And so on and so forth. This is the sentence I want to highlight. Shall I refuse my dinner because I do not fully understand the process of digestion? Okay. Do you like it? So we can stop here. And the next time lecture, you should not miss, okay, at all. I'm going to talk about very important concept about realization, okay? And if you miss, it's hard to pick up by yourself or simply by watching the recorded lecture. It's different. So, questions? I think my way of delivering convolution is probably, I delayed that explanation until today. So probably it's a better way. Okay, I'm stop sharing to see any other questions in the chat box. No, great. We have 44 students. Very good. Thank you very much. Then I want to say goodbye to you, and I'll see you Friday office hour. Okay, bye-bye.